Hello everyone, this is Lecture 7 of ComSci 142, Greedy Algorithms. In this video, we will discuss greedy algorithms and use them to solve problems such as activity selection, set cover, Huffman encoding, and fractional knapsack. The greedy strategy is the third algorithm design paradigm that we will discuss in this course. So sometimes, greed can be good. In algorithms and in life, you need to take the chance as the opportunity arises. So sometimes you need to be greedy. One example of such greedy strategy was shown in Gale-Shapley algorithm that solves stable marriage. Okay, so in that algorithm, the men, when choosing who to propose to next, just went for the best girl possible, meaning she's high up in his ranking and he hasn't proposed to her yet, or she hasn't rejected him yet. Okay, so the best possible so far for him. Okay, so that is greedy because he's trying to go to the best possible choice currently, right? So by being greedy, you take as much as you can as often as you can. Okay, but this is a very short-sighted decision making. Okay, you're just looking at what is currently the best so far, and you're not looking at it in a long-term manner. Okay, so you make the choice that appears best currently, so that is very short-sighted. Okay, emphasis on the word currently, because what appears best now might not be the best in the long run. Okay, so for example, when you're playing chess, if you tend to make too many short-sighted decisions or moves, then you end up losing most of the time, right? You need to think long-term in chess. You need to think a few steps ahead, right? But if you only do what is like the best so far for the current situation, that might be a trap set out by your opponent, and that might cause you to lose, right? So you can't be greedy and you can't be short-sighted in chess. But in Scrabble, on the other hand, then you can just be greedy, right? You can just put out the best possible word that you can get for now, because anyway, you don't know what will happen later on. So you might as well just give it your best word, right? So in Scrabble, you can do the greedy strategy and you can win. Okay, but not in chess. Okay, so how does this apply to optimization problems? In optimization algorithms, there is a sequence of steps that you need to follow, right? And in each step, there is a choice of which step would lead to the optimal solution. Because if there is one step there, one misstep that you did not choose, or sorry, if one step is not optimal, then obviously the whole path will not be optimal anymore, right? So at each step, you have to choose which one is optimal, like what we did in minimum edit distance, longest common subsequence, longest increasing subsequence, and the knapsack, right? Remember, in the small sub-problems, we chose which one is the minimum or which one was the maximum out of the sub-problems in order to get the optimal value for that sub-problem as well, right? For sub-problems, however, if you do dynamic programming, it's too much, right? It's overkill, okay? Because you can do away with just using a simpler algorithm using the greedy approach, and it can even be more efficient if you do this, okay? This is for some optimization problems, not all, okay? So we'll see later on what some problems are solvable by using greedy strategy, and it's more efficient than applying dynamic programming. Okay, so in greedy algorithms, we build up the solution piece by piece. Okay, so and by building it piece by piece, what we do is we choose the next piece or the next part of the solution that offers us the most obvious and immediate benefit. So that is the greedy part of the strategy. Okay, it gives you the best benefit right now, okay, without thinking of the long-term ramifications or effects of picking that one. Okay, So it's only a locally optimal choice. So it's locally optimal, meaning it's only optimal for that current environment. Okay, of course your hope is that it will lead to a globally optimal solution, meaning it's also optimal in the long run, or in the big picture. Okay, but you can only hope that that is the case. Okay, because most of the time locally optimal choices are not the same as the globally optimal choice. Okay, in some cases it coincides, but we cannot assure that one. So we can only hope that your locally optimal choice also leads to the globally optimal solution. Okay, so this gives us the question, is it always optimal? Although I've kind of answered that already in the previous slide. For some problems, as I've said, it gives us the optimal solution, but in general, it's not guaranteed to be optimal. So as I've mentioned, we can only hope that this locally optimal solution can be globally optimal as well. But we cannot guarantee that, and that is the disadvantage of greedy algorithms. Okay, the advantage is it's easy to do, but the disadvantage is it's not guaranteed to be optimal all of the time. Okay, but for some problems, it's optimal. Okay, so we have this old meme: I don't always yield an optimal solution, but when I do, it's awesome. So that's greedy algorithms. Okay, so yeah, so if greedy algorithms don't give us the optimal solution all the time, why do we need to study it? Because it's easy to do, and because it's a good starting point to solve optimization problem. So if you have an optimization problem and you don't know what to do, you don't know which strategy to use, you can start by being greedy first. Okay, so apply greedy strategy and then find out what the baseline solution values are, and then that is where you could start your solution, and then you can improve on that. Okay, so you can improve using better techniques, but at least now you can see what is the baseline. So you can see, for example, if you applied greedy on minimum edit distance, maybe you say, okay, in greedy I had a minimum edit distance of 10, so maybe it would the solution could be better than that. Okay, so that is at least your starting point. Okay, so you can choose other techniques like branch and bound, constraint programming, local search, and other techniques, but greedy algorithms is your starting point. Okay, so to do the greedy strategy, you have two ingredients. You have the greedy choice property and the optimal substructure property. So we've already seen this optimal substructure property in dynamic programming, so it's more or less the same also in here, but we'll focus on the greedy choice. Okay, so it's pretty straightforward. The greedy choice is you make the locally optimal choice. Okay, so when faced with the option of picking which choice to pick, you pick the locally optimal choice. So you get greedy, and you take the choice that looks best in the current problem, and you don't consider results from other sub-problems. So you don't consider the past, you don't consider the future, you only consider the now. Okay, this sub-problem, what is this sub-problem telling me? So this sub-problem is telling me that I have to choose this one, so because this looks best right now, and that is essentially what you do in greedy. Okay, so you focus only on the current sub-problem. Okay, let's contrast that with what dynamic programming is doing. So in dynamic programming, the choice at each step depends on solutions to older sub-problems, right? Remember, we had to consult previous sub-problems answers in order to decide what the current sub-problems value would be, right? That was dynamic programming. We did that through tabulation. Okay, but in greedy, the choice is what is the best choice at the moment. Okay, so you don't consider the past or future choices. So that is one difference of dynamic programming and greedy. Dynamic programming looks at the past, greedy does not. It only focuses on the now. Okay, and dynamic programming also kind of plays it safe. It's segurista in a way, because it solves all of the smaller sub problems in order to solve the bigger sub-problem. Okay, so it solves all of the sub-problems even in tabulation. Whereas in greedy, you're kind of a risk taker. Okay, like YOLO attitude. Okay, so bahala na, if whatever happens happens, but I will choose this best looking choice for now, and whatever happens later, just live with the consequences, right? So that is also one difference for dynamic programming and greedy algorithms. Okay, the last difference is that for dynamic programming, you build from bottom up, you build going up, right? Because you start with the smallest sub problem and use the answers to those small sub problems to have the answer to the bigger sub problems, right? So start from the bottom going up. But in greedy, we follow the top down direction. So we're trying to reduce the sub problems. Okay, so the original problem, you will reduce that to a smaller problem until it's already solved. Okay, so that is another difference between the two. Okay, dynamic programming is bottom up, greedy is top down. Okay, so to make your greedy choice, the essential thing for your greedy algorithm is something called a heuristic. Okay, so what is a heuristic? A heuristic is a function that gives the score to your choices. Okay, so you're supposed to choose what the best choice is, right? But how do you know which one is the best? So of course you need to score them. You need to rank them. You need to give them an objective value that tells you this one is the best choice. Okay, so that is a heuristic. Okay, so that function will compute the scores, and you use those heuristic scores to make the greedy choice. So it's, if you choose the best, it's either min or max depending on the problem, right? If you're minimizing or maximizing a certain value. Okay, so a heuristic again is basically just a function that scores your choices, and this will allow you to make your greedy choice. Okay, so that is the first ingredient, greedy choice. The second is optimal substructure. So it's similar to optimal substructure in dynamic programming. So the optimal solution to the problem is from the optimal solution of sub-problem. So contained within the optimal solution to the bigger problem is the optimal solution to smaller sub-problems. Okay? And for formal proof that it is optimal ang greedy choice mo, you need to prove that your greedy choice stays ahead. That means that no other choice is better. Okay, so we'll in some instances we'll show that it stays ahead, but in some instances we'll just accept it for now. We won't go through the proof formally. Okay, but I'll just give you an intuition of what makes it the best choice to make. Okay, so those are the two ingredients, greedy choice and optimal substructure. So let us now go through our first problem, activity selection. So to introduce the activity selection problem, imagine that the semester is over and you are now allowed to like take a small vacation or a quick vacation. Okay, assuming of course that the COVID pandemic travel restrictions are already somewhat not as strict, right? So just imagine that you were able to go on a vacation. So during that vacation, of course, there's a lot of activities that you could go to. Okay, so as a tourist, you ask yourself, which activity should I do, right? Because I really need to unwind. I'm really stressed out by the previous semester. Okay, so among these activities, of course, there would be overlapping activities, right? So there could be like banana boat from that's only available from 8 to 10, and then riding the ATV from 9 to 12. So there could be some overlaps in the activities, and you can only choose one among those overlapping activities. So and your goal is to try to maximize the number of activities as much as possible, just so that you can also maximize your vacation, right? So among these overlapping activities, which one should you do so that you have a lot of activities to experience. So that is uh, the gist of the activity selection problem. Okay, so formally we'll define activity selection as follows. For the input, we were given a set of activities. We will call that set A, and there are n activities in total. Okay, and each activity has a start and finish time. Okay, so the start and finish, start ranges from 0 to finish, and so on. So 0 is less than equal to start, start is less than finish. Okay, so, and then the output would be, okay, the maximum size subset of mutually compatible activities. Okay, that seems like a mouthful, but what does that mean? Okay, so maximum size subset just means as many activities as possible. So choose a collection of activities that's as many as possible. Okay, that's what maximum size subset means. So a collection of activities wherein it's as many as possible, and it also has to be mutually compatible. So by mutually compatible, we just mean that it doesn't overlap. Okay, so because if you've already done the 8 to 10 one, of course you can't do the 9 to 12, right? Because you're still in the middle of doing the 8 to 10. So it should be mutually compatible. So some applications of this problem include scheduling problems in different fields, right? Different areas. Okay, so formally, let's define compatible activities. X and Y, two activities X and Y are compatible if the intervals the intervals for X and intervals for Y do not overlap. And that means that either X finishes before Y, so less than or equal to the start of Y, or Y finishes before or during the start of X. So it could be the finish of X is at 10 and then the start of Y is at 10, so they don't overlap, right? Or this one finishes at 9 and then this one starts at 12, so there is no overlap as well. Okay, so you can even draw a timeline of activities to visually to see it visually. If see it visually, so seems redundant, to see easily if there are conflicts in the activities, set of activities. Okay, so let's see a quick example of compatible activities. So in this one, X starts from 1 to 4, and then Y is from 3 to 5, Z is from 5 to 7. So are X and Z compatible? Yes, because this one ends at 4, this one starts at 5. Are Y and Z compatible? Yes, because this one ends at 5, this one starts at 5. So it's still compatible. How about X and Y? They're not compatible because this one ends at 4, but this one already starts at 3. So they can't be, they are overlapping. Okay, so they cannot be compatible activities. Okay, so before we go to the greedy strategy, let's look at the brute force approach first. Okay, so for the brute force, we will just try all possible activity combinations and reject those combinations with conflicts. Okay, because we don't want any conflicts within our set of activities, and we'll just return the combination with maximum size, meaning the most number of activities. So seems pretty straightforward, but how long will this run? If there are n activities, how many possible combinations of activities are there? Okay, there could be 2 raised to n combinations, because if you have, let's say, 3 activities, how will you do the combinations for 3 activities? A, B, and C. So you can do just A itself, just B itself, or just C itself. You can do A and B, A and C, B and C, or you can do all 3, or you can do nothing, right? So how many active combinations are there? We have 3, 6, 8, and 8 is 2 cubed, where n is 3 here because we have 3 items or 3 activities. So you have 2 raised to n possible combinations, right? So that is exponential. Okay, so and the time it takes to check if the combination is valid is also O of n, because at most you have n activities in the combination, and you need to check one by one if there is overlap, right? So the total running time would be 2n times O of n, or n times 2 raised to n. So it's more than exponential, it's n to n. Okay, so it's pretty bad. Okay, so let's try this time with the greedy approach. So how will we solve activity selection using greedy approach? So first, we will greedily pick the activity, and then we'll add that activity to the solution. And once we add that activity to the solution, of course, we'll have to remove activities that are conflicting with it, right? Because if it's in conflict, we cannot add it to our solution later. Okay, so we'll have to remove conflicting activities, and then we'll repeat until no more activities left. Okay, but the big question here is, how do we greedily pick the activity? Okay, that is the main thing you need to focus on when doing greedy algorithms. What is the greedy choice? Okay, so we have some heuristics here that we could try. First is pick the activity that starts early. So we call that the early start heuristic, or it could be the one that ends early, or it could be the activity with the shortest length, or the one with minimum conflicts. So before going forward with the video, pause it here and try to think first for yourself which one is the best possible heuristic to use. Okay, so try to think or try to pick among the 4 which one do you think is the best greedy heuristic to use, so that we'll have as many activities as possible. Okay, and then after you have picked your choice, let's find out later if you were right or wrong. Okay, if you got it wrong, no problem, but if you got it right, then at least you have some bragging rights maybe, or I don't know. Anyway, so let's go through each greedy heuristic one by one and see why they would work or not work. Okay, so first, let's look at early start. Okay, the early start heuristic will select the activity that starts the earliest. So this seems reasonable, because if you start early, then you might have more activities to do, right? So we'll pick the one with the smallest start time. Now, do you think this gives the optimal solution? Well, unfortunately, it does not. Okay, because it does not. So it does not guarantee an optimal solution, because there is a way for you to have a suboptimal solution while choosing early start. So a counter example would be an early activity but has a long interval, right? So it could start early but it takes the whole day, right? Like activity A here. It started first but it takes too long. Okay? So the greedy choice here would be to take A because of the early start, but the optimal solution would be to pick B, C, D, E, right? Because if you pick A, of course you cannot pick B, C, D, E anymore, because they are in conflict, right? Because they are overlapping with each other. So early start does not give you a optimal answer. Okay, so your goal is to have as many activities as possible. The worst case is when the earliest activity lasts the whole day, right? So the greedy solution in the previous one only has 1 activity, but the optimal has 4, right? So that is a counter example of when it could be suboptimal or not optimal. Okay, so early start is not the answer, unfortunately. How about shortest length? Because if our problem here was that the earliest activity took too long, how about if we pick the one with the smallest interval, right? Because if you have a small interval, then you're only taking less time, right? So you have like more time to do other activities. So that is also like a reasonable heuristic. Okay, so you select the activity with the smallest interval or the smallest finish minus start, because that is the duration of the interval, right? So you take the difference between finish time and start time. Does this give the optimal solution? Well, it still does not. Okay, so it is better than early start, but it's still suboptimal. Okay, so I'll show you a counter example again. What if the shortest activity starts at noon? So how about this one, activity A? It's the smallest activity or the shortest activity, but if you follow this heuristic, you will only pick A here because it's in conflict with B and C. But the optimal solution would have been picking B and C, because then you can do 2 activities compared to 1, right? So the worst case is when the shortest activity is in the middle and it conflicts a lot with other activities. Okay, so in the greedy solution we can only pick 1, but the optimal would have been 2. That would have been better, right? So the problem here naman is that it has conflicts with others. So what if this time we try selecting the activity with minimum conflicts, right? So earlier we tried to patch the problem by selecting the small duration, but this time, since the small duration had a lot of conflicts, what if we try the activity with minimum conflicts, right? So it has it doesn't overlap with a lot of activities. Okay, so the one with few incompatible activities, so X and Y has a conflict if you can't do Y if you do X, something like that. Okay, so they overlap basically. Does this give the optimal solution? Well, it still does not. Okay, so it's better than the 2, but it's still suboptimal in general. So I'll show you a counter example, another counter example here. So in this one, okay, change the color. Okay, so for this one, if we're picking minimum conflicts, so let's give them the grade. So the heuristic is minimum conflict, so let's count the number of conflicts each activity has. So for A, how many conflicts does it have? It has 3 conflicts, right? Conflict with E, F, and G. B has 2 conflicts. C also has 2. D has how many? 3, right? And then for E, F, G, they have E has conflict with 1, 2, 3, 4, right? So all of them has 4 conflicts actually. So then this one also has 4 conflicts, right? And then for H, it also has 2. Okay, but okay, so if we do this, sorry, B does not have 2. Sorry, this one is wrong. B has 1, 2, 3, 4. 4 conflicts. Sorry. C also has 1, 2, 3, 4. Those are the conflicts because they are overlapping here and with here, right? Same with here and here. So all of those are conflicts. 1, 2, 3, 4. And then same with C. Okay, so if we do the minimum conflicts, which one will we pick first? So we will pick H, right? Because it has the minimum conflict of 2. So if we pick H, then we cannot pick B anymore because it's in conflict, and we cannot pick C anymore, right? So if that's the case, the next choice would be A with 3 and D with 3, right? And if you pick A and D, then of course E, F, G, I, J, K won't be considered anymore because they're in conflict with A and D. So in total, you can only choose 3 activities. You have A, H, and D. Okay, but what would have been the optimal solution? The optimal solution would have been this 4, right? So optimal solution has 4 activities, but our greedy strategy using minimum conflicts will only have 3. Okay, so it's still suboptimal. Okay, so how about the last heuristic, which is early end. So you select the activity that ends the earliest. So you select whichever has the smallest finish time. Does this give the optimal solution? Yes. This one is the heuristic that gives you the optimal solution for activity selection. So if you chose early end as the heuristic earlier, and congratulations, you answered it right. Okay? Now, why do you think this one is the best heuristic, or why does it give you the best choice? Because the idea is, if you end early, then you become free as soon as possible, because you end, or you end one activity early, so you have more time now to do other activities. Okay, if you are free early, then you have more time to do other activities. So we will choose the early end. Okay, early end heuristic as our heuristic for the greedy activity selection. So what we will do is, first we will sort the activities by finish times. Okay, so we'll sort it in ascending order, so that the ones that come first are those that end early. Okay, and then for each activity, skip the activity if it's in conflict with the previous activity's end time. Okay, otherwise you add the activity to S, and then you use the activity's current end as the indicator for when you need to skip other activities. Okay, so it's pretty straightforward, right? And it's also straightforward to analyze. So for this one, if we need to sort by finish times, so we could use merge sort. This will run in O of n log n if we use merge sort. Okay, and then for activity in A, so we'll have to go through each activity, and if there are n activities, this will run in O of n. Okay, so n log n plus n, the running time would be O of n log n. So the sorting is n log n, the for loop is O of n, the running time is n log n because this one is bigger. So if you add n log n plus n, the n log n here would dominate. So the sorting is actually the bottleneck of the algorithm. Okay. For the memory, it's constant because we did not use extra memory for this one. Okay, so let's see an example of this one. So this activity has 11. Okay, so we have 11 activities here. These are their start and end times. So what would be the best set of activities to choose so that we have the maximum number of activities? So first, what we need to do is sort them by their end times. So let's sort them by their end times, or by their finish times. So they are now sorted according to their finish times. And we'll just go through each activity. So first, we can pick this one because there is no activity chosen yet. So we will do activity B from 1 to 4. Now let's go to the next activity. We will skip this because it's in conflict with the end of the current activity that we have, which is B, right? A also will be skipped because it starts before we end B. Now F can be added as an activity because it starts after nag-end na si B, right? So 4 ang end and it starts at 5, so they are compatible. So now our current activity is F with 5, 7. So for D, we will skip this because 3 is less than 7. Okay. We'll also skip G because the starting 5 is before nag-end si F. H will also be skipped for the same reason, but J can be added as an activity because 8 starts after F finishes at 7. Okay, so we'll add J, and then our new end time that we'll need to look now would be 11. So I would be skipped because it starts at 8. C would be skipped because it starts at 2 and we end at 11. And then K is allowed to be added because 12 starts after 11 is ended, right? So we now have 4 activities that we could do, and that is the maximum set of activities that you could do without overlaps. Okay, so that is activity selection. Pretty straightforward, right? You just need to sort them by their end times and then go through each activity one by one, and you skip the activities that are in conflict with the current activity that you have. Okay, so that's it. So this is the solution, size 4. Okay, so let's now go to our second problem, which is the set cover problem. So let's discuss a scenario first to introduce the set cover problem. And let's imagine that you've already graduated, right? You're already, let's say, 10 years or 15 years from now, and then you became a mayor of your town. Okay, hopefully you'll be a good leader. You won't be corrupt. But yeah, you became a mayor of your town, and your project, your first project is about education because there are no schools yet in your town. So let's say your town is uneducated, and that's probably why you won in the first place. No, that's not it. But anyway, so let's imagine that the town doesn't have any schools yet. So your goal, of course, is to build schools, right? But you also don't want the students to like suffer and travel far away, so they could go to a school. So your goal is the students shouldn't travel more than 5 kilometers. So for each barangay, there should be a school within a 5-kilometer radius. So something like that. Okay? But you also don't want to build a lot of schools, right? You want to minimize the number of schools because, of course, you're also on a limited budget. So how would you do this? Okay, where would you build the schools so that it would reach all possible students, right? So within 5-kilometer radius, but you're also minimizing the amount of schools that you're building. Okay, so if you had unlimited supply, of course you could just build one per barangay, but it's not feasible, right? So which barangays would you build your school in, such that students within the 5-kilometer radius can travel to that school, and all barangays are covered, basically. Okay, so that is more or less how the set cover problem is structured. So formally, for the set cover, we have an input. We'll call this the universal set of items, called U. Okay, and we have n items here, okay, in the universal set. And then we'll also have a collection of subsets. We'll call that S, from S1 to SM. So S1, S2, S3, S4, up to SM. So there are M possible subsets. Okay, where each subset is, of course, a subset of the universal set. And the crucial part here is that the union of all the subsets equal to the universal set. So that means that all items in the universal set is part or covered by at least one subset in S. Okay, so that if you take the union of all subsets, you'll still get the universal set. So no item is left uncovered. Okay, so now how about for our output? For our output, we will give the smallest combination of subsets, okay, such that the union of subsets is the universal set still. So what does that mean? This means that we will choose some subsets in S, but in such a way that the combination of the subsets still equals the universal set, but we'll try to minimize that number as much as possible, the number of subsets that we have. Okay, so combine the subsets to cover the universal set, and that means that we need to cover all elements in U at least once. Okay, so that is what we mean by the set cover. choose some subsets out of let's say we have let's say we have 10 subsets, so we'll choose the minimum number of subsets in such a way that those subsets still cover all universal items if we take the union. Okay, so for example, we have the following. So let's say that your universal set is 1, 2, 3, 4, 5. So you have 5 items in your universal set, and then you have 4 subsets. So S1, S2, S3, and S4. And then for S1, it has this subset, S2 has this, S3 has this, S4 has this. What would be the optimal solution for this set cover? The optimal solution would be S1 and S4 because, okay, if you chose S1 and S4, you would have 1, 2, 3, and 4, 5. And that covers the universal set already. Okay? If it was just S1 and S2, it would only cover 1, 2, 3, and then 2, 4. So we'll add 4 here. And that does not cover the whole universal set. So this one is not a valid set cover. Okay? We could do S1, S2, and S4. And this will give us 1, 2, 3, 4. And then from S4, we have 5. So this one is a valid set cover, right? Because it covers the universal set. But this is not optimal because we have how many? We have 3 items in here. One, S1, S2, S4. The optimal solution is this one because it only has 2. So it has the minimum number of subsets. Okay? So we'll try to choose few subsets as possible. Okay. So let's see another example. In this one, the universal set would be the letters. So A, B, C, D, E, F, G, H, I, J, K, L, M, N. So we have 14 in total, right? 14 items. And then the sets would be, the subsets would be the squares that cover them. So the purple one is one subset. So for the purple, that subset would be A and H. For the green, that would be B, C, I, J, right? Because that is enclosed in the green. For the blue, we have D, E, F, G, K, L, M, N. So it has 8 in total. And then we also have the red and the orange, but I won't write that anymore since there's too many. So for red, it's A to G, and then for the orange, it's H to N, right? So what would be a set cover solution here? One solution would be to take purple plus green plus blue, right? Because if you take the 3 subsets here, this one, and this one, that will cover all items, right? That is one solution. But another solution is just take red plus orange, because the red set and the orange set here will also cover everything. But which one is the optimal solution? Well, the optimal solution is this one, because it only has 2, whereas this one has 3 subsets. Okay, so our goal is to have as few subsets as possible. And in the introduction setting, how would we formulate that as a set cover? So the universal set would be all barangays. The subsets would be for each barangay, the barangays within distance less than or equal to 5 kilometers, so within 5-kilometer radius. And then your optimal solution would be, where do you build the schools? Okay, so which set of barangays would give you total coverage, meaning everyone is covered within a 5-kilometer radius, but it's also as few as possible ang barangays. Okay, so that is set cover. And there are some variations to the set cover problem. So you also have the weighted set cover problem, wherein each subset has an associated cost. Okay, so maybe this subset has a cost of 10, the other subset has a cost of 20, and instead of minimizing the total number of subsets, you're trying to minimize the total cost of subsets. Okay, so we call that the weighted set cover problem. There is also the optimization version of the set cover problem. So in the optimization version, you're looking for the actual optimal solution, so the best possible solution. But there is also the decision version problem. And in the decision version, you're just asking, does a solution using less than or equal to k subsets exist? So can I have a solution using only 4 subsets or 5 subsets, something like that? So it's not necessarily the optimal solution. You're just asking whether 5 or 6 or whatever, however many subsets is possible to cover everything. Okay, so that is the decision version. The bad news, however, is that the set cover decision version is already NP complete. So remember the knapsack problem wherein it was also NP complete ang decision version. Set cover is the same way. And the optimization version is even worse because it's NP hard. So it's even harder than the decision version, which is only NP complete, right? So again, I already mentioned this in the previous video, but to recall, NP problems are those that currently they only have the brute force or the exponential enumeration. So you have to try all possibilities, and that is what is guaranteed to give you the optimal solution. Okay, there is no known polynomial time algorithm so far for these types of problems, so it's still an open problem. So for now, and when we say NP complete, it's one of the harder NP problems, and then if it's NP hard, it's even harder than NP complete. Okay, so set cover was even one of the original 21 NP complete problems made by Karp in 1972 when he first discussed this NP complete problems. Okay, so one of the original NP complete problems. And okay, so if set cover is an NP hard problem, why are we discussing it in the greedy scenario? Because well, since it's already an NP hard problem, there is no known polynomial time algorithm so far. So what we can do is just approximate. Okay, we can't give the optimal solution all the time. So what we can do is just give an approximately optimal solution. Okay, so meaning it's not optimal, but it's close to the optimal value. Okay, and sometimes that's good enough. You don't need to be optimal all the time, right? So because if you really force it to be optimal, then it will take too long to compute. So for greedy, we can get the approximate optimal solution, and this is an example of a greedy solution that is suboptimal. Okay, so we mentioned early in the introduction of greedy algorithms that it does not guarantee an optimal solution, right? So this is one of those instances wherein it's not optimal all the time. So earlier in activity selection, we were kind of lucky that the greedy solution gave an optimal answer, but this time we're not as lucky. Okay, so however, this is not greedy's fault because the problem is already NP hard, so we really can't do anything about it for now. Okay, so let's see. So set cover is an example of a combinatorial optimization problem, and basically combinatorial optimization tells you to find the best combination of items, and it's kind of challenging because this is not just like one solution, but it's a combination of items, right? So it's not just like what is the minimum edit distance, something like that. You have to find the combination of items, like knapsack. Knapsack is a combinatorial optimization problem as well. And set cover was instrumental to the development of fundamental techniques for approximation algorithms because because it was really hard to do. It was NP complete, so a lot of people were trying to solve it, and they came up with techniques for approximation algorithms. So it was crucial in developing approximation algorithm techniques. Okay, so let's now go through the brute force approach first before we look at the greedy strategy. So first, for brute force, we need to try all possible subset combinations, right? Try all possibilities, and we'll reject those combinations whose union is not equal to the universal set, meaning they don't cover all items, because that is not part of the solution, right? The solution has to cover all items in the universal set. And then we'll return the valid combination with minimum number of subsets. So whichever has the least number of subsets and is also valid, that would be the solution. Okay, so seems pretty straightforward, but again, the problem here is that there is just way too many combinations. So if you have m subsets, there would be 2 raised to m combinations. So we've been going through this repeatedly, no? So number of combinations is 2 raised to n if you have n items. So if you have m subsets, that's 2m combinations. And it would also take O of n time to check if the combination is a valid na set cover, because you need to check each item in the universal set if they are covered by one of the subsets. So if there are n items, so you have to traverse each item. Okay, is this covered by one of the subsets? So that's O of n. Okay, and so the running time would be, if there are 2m combinations and each combination takes O of n, that would be n times 2m. So it's also more than exponential. It's pretty bad. So we have to improve on it. Okay, so let's now look at the greedy approach for the set cover problem. So as usual, we will do the greedy choice. We'll greedily pick a subset. We will add the subset to the solution and add the subset items to covered items, because once we have added that subset to the solution, its items should already be covered, and then we'll repeat until all items are already covered. So the crucial part here again is just step 1. How do we greedily pick the subset? Okay, so that is always the key choice in the key point in greedy algorithms. What is your greedy choice? So we'll take a look at 3 different heuristics, and we'll improve on each one as we go. So first, if you can't think of anything, how about if we just take the default order? So if it was S1, S2, S3, S4, let's just take it in that order. Okay, so take the subsets following the default order, because maybe you still cannot imagine what the possible heuristics are. So at least you have something to start with, right? And then you just stop if all items are already covered. So the worst case is if you use all m subsets, right? So as I mentioned, it gives us a starting point to improve upon. So let's see an example of this one. So okay, this one's already done. Okay, so we're using the default order heuristic here, and the universal set is from 1 to 9, and then we have the 6 subsets here. So S1, 1 to 4, S2 has this, S3 has this, and so on. Okay, so if we visualize that one, it would look something like this, right? So the universal set is here, 1 to 9, and the subsets are here, right? So for example, S2 has 1, 2, 3, 6, 7, and then 9. Okay, and then these are the uncovered ones for now. So if we do go through this in the default order, of course we'll pick S1 first. Okay, so this one would be our first score, because the order would just be like this: 0, 1, 2, 3, 4, 5. So just in this order. So we'll pick S1 first because that's the best score. So this time 1 and 4 are already covered, and the next we'll proceed with S2 because there are still uncovered items. So S2, will cover a lot of things. So it will cover 2, 3, 6, and 7. So only 5 and 8 are left now. But the scores remain the same. We'll go to S3 next. S3 does not really uncover any new items, so we'll just go through the next one. S4 covered this one, 8. But we still have 5 left uncovered, so we'll proceed to S5, and now everything is covered. So all in all, we chose 5 different subsets. Okay, so we chose 5 subsets and we covered everything. So is that the best that we can do? Well, not obviously. It's not the best answer, but at least it's a starting point, right? So that is our solution. It uses 5 subsets, but it's better at least than using all 6 subsets, right? It's better than the worst case. So let's try to improve on this and use the second heuristic, which is by choosing the most number of elements first. So that seems like a good idea, because if you choose the most elements first, then you will uncover many items quickly, right? So for example, if we reset this one and choose most elements covered, okay, so this is the sets and the subsets again, and if you compute their scores, it will take into account how many items do they have. So for example, here it only has 2, this one has 6, this one has 5, this one has 3, this one has 5, and then this one has 4. The rationale behind choosing the most elements is if you pick 6, for example, here, then you would immediately cover 6 items, which is already a lot, right? So that would maybe make your job faster, because you're covering a lot of items quickly. Okay, so that seems like a good idea. So let's try it here. So after computing the scores, we will pick the best score first, so most elements. So we'll pick 6 first, S2. Okay, so when we pick S2, it will uncover 1, 2, 3, 6, 7, and 9. And then the next in line, it would be either S3 and S5, but if we choose the tiebreaker as the default order, maybe we'll choose S3, right? Because anyway, tied na sila 5. So when we do that, however, it doesn't really uncover new items, so it still remains the same. And next, we'll choose S5. Okay, so in S5, we will have we will uncover more items, but there is still 1 left. Then after that, based on the scores, we will pick S6 because it has the next best score. And after that, everything is now covered. Okay, so we now have everything covered, and we only used 4 subsets, right? So that's already better than your previous heuristic, which was the default order. So uses 4 subsets. At least it's better than heuristic 1, but we can still improve on this. Okay, so if you remember earlier, the problem here, so let's redo that again. The problem here was that, okay, so picking 6 was a good idea here, right? But in the next iteration, when we picked 5 here, the score 5 here is actually already irrelevant, because even if this has 5 items, in the scheme of uncovering or covering uncovered items, it actually doesn't add anything new, because this one, 2 is already covered, 3 is already covered, 6, 7, and 9 also already covered, right? So the score 5 here is already irrelevant. And what would have been better would be picking something like S5, or maybe, yeah, S5 would have been better in this scenario, right? So our third heuristic would try to improve on that by instead of picking the most number of elements, we'll pick the most number of uncovered elements. Okay, so we'll be updating the scores as we go. So it's similar to heuristic number 2, but we'll update the subset priority by considering only uncovered items. Because if they're already covered by the previous subset, then it would be kind of irrelevant already to count the same item in the score, right? So it should not have a bearing anymore on the score, especially like for example S3 here. It has a score of 5 in most elements, but it doesn't really have a bearing on the uncovering of items since all of its items have already been covered already by the previous subset. Okay, so that is how we'll improve the heuristic number 2, and the idea behind this one is that many uncovered items will be covered, which is a good thing, right? So let's see this one again. Let's reset, and this time let's use most uncovered elements. Okay, so we'll first compute the scores. So at first this looks similar to the first one because everything is uncovered for now. So we'll still pick 6 S2 here because it has the best score, but this time we will recompute everything, the scores. So recompute the scores. For S1, isa na lang ang uncovered niya, only 4, right? For S2, everything is already covered. For S3, already covered everything. S4, only 1. For S5, it has 2. And for S6, it has 1. Okay? So based on these current scores, we will pick S5 next because it has the best possible score. Okay? And then it will cover more items. And since there's still an uncovered item, we will recompute the scores again. And this time, only S4 and S6 has an item that is uncovered. So maybe we'll choose S4 in that case. Okay? And then after that, everything is already covered. So this time, we have chosen only 3 subsets. Okay? So that's also better than the previous one with 4 subsets, right? So we've been constantly improving on the heuristic. So we have a solution of 3, uses 3 subsets. It's better than the first 2 heuristics, but this is not the optimal solution because the optimal solution would be what? So what is the optimal solution here? The optimal solution would have been to pick the last 2 subsets, S5 and S6, because they are actually complementary, because whatever is blank here in S5 is not blank in S6. Okay, so if you pick this, if you merge everything, you will cover all items. So just this 2 is enough to cover everything. Okay, but our first heuristic gave us 5 subsets, our second heuristic gave us 4, our third heuristic gave us 3, but the optimal solution was just 2 subsets. Okay, so as I mentioned, for set cover, the greedy heuristic is not optimal. But for us, what we'll do is the best greedy heuristic that we'll have is the heuristic number 3. Okay, most uncovered element. So it's close enough to the optimal solution. Okay, so it's the best out of the 3 that we discussed. So we'll select the subset that covers the most number of uncovered elements so far. So you have to recompute the scores once some items are covered already. Okay, so you have to update and make sure that you're only counting the items that are still uncovered. Okay, and choose the subset that has the most number of uncovered items. Okay, so that's it. If you put everything in a pseudocode, it will look something like this. So you have an uncovered set, which is everything. For now, everything is uncovered. And then, while uncovered is not yet empty, select a subset in S that maximizes the size of subset intersection uncovered. So meaning, which subset has the most uncovered items. So maximizes. And then you subtract that subset's items from the uncovered, so those are already covered, and then you add this subset to your solution. Okay, and then you repeat that until all items are covered. So At the worst case is if we use all m subsets, so this will have at most m iterations, and when we select, we're finding the max of all subsets, so we're looping through all m subsets, so that also takes O of m. So if you have m iterations for all subsets and O of m per iteration when taking the max, your running time is O of m squared. Okay, so m squared ang running time, so it's polynomial, and the memory is O of 1, it's constant because we're not using any extra memory. Okay, so let's see one more example. Let's just go through this. If we choose the most uncovered elements, so let's use that as our score. So for S1, what would be the score so far? Score would be 1, 2, 3, 4, 5, 6. This one would have 5, score of 3, score of 3, score of 5. So if these are the current scores, we would choose S1 first. Okay, so S1 would be chosen. So we will have to cover 0, 1, 2, 3, 8, and 9. Right? So let me change my color first. Okay, so after that, after we've chosen S1, let's recompute our solution, our scores. So this one would have 0 anymore. So 0, 1, 2, 3, 8, 9. So 1, 2, 3, 8, 9 are already covered. Okay, so only 4, 5, 6, 7 remain. So 4, 5, 6, 7, and also 0 should be out. So by recomputing their scores, they should have 0 already. This one will have 2, this one will have 3, 3, and 2. So the best one is either S3 or S4. For the tiebreaker, let's just choose S3. So it will cover 4, 5, 7, right? 4, 5, and 7. So 4, 5 are done, as well as 7. 4, 5, 7, 5, 7. So finally, our scores would be 0, 0, 0, 1, 1. So since there's a tie, maybe we'll just choose S4, and then now everything is covered already. So our solution, if we use this heuristic, was S1, S3, and S4, right? But what would have been the optimal solution? The optimal solution would have been just S2 and S5, because if you take S2 and S5, you would have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which is everything in the universal set. Okay, so this is the optimal solution, but our greedy solution gave us 3 subsets, but that's close enough, right? 3 is close to 2. So yeah, and then if it was this one, what would have been our I've already shown you this earlier, right? If it's most uncovered element, so ang sa purple would have 2, this one would have 4, this one would have 8, this one would have red would have 7, this one will also have 7. But because of the max score, we will pick blue with 8, right? We'll pick blue with 8, and so if we have 8 here with blue, 7 cannot, their scores would be updated, right? So if all elements in blue are already covered, so these ones are already covered, right? This one, this one, this one. So I'll encircle the covered items. So let's recompute their score. So blue would have 0, this one would still have 4, this one would still have 2, this one would only have 3 now, right? Because these 4 are not counted anymore, and then same here, 3. So if that's the case, we will pick this one, with 4. And so this would be covered. And this one would have a score of 0. And then this one would still have a score of 2. But this 2 would have a score of 1 and 1. So we'll select this one. And so the greedy solution would have been the blue, green, and purple. But as we mentioned earlier, the optimal solution would have been the red and the orange, right? So we can see that our greedy strategy is close to optimal, but it's not optimal. Okay, so the greedy set cover algorithm gives us a good approximate solution, and that is the trade-off that you need to take, because again, this is an NP complete problem and NP hard for the optimal version, optimization version. So you don't have the exact optimal solution, but at least you can solve it quickly. Because if you want to find the exact optimal solution, then you would have to go through the brute force. Okay, and brute force takes more than exponential time, so it won't exactly be quick. Okay, so that is the trade-off that you need to have. Now you can also do some improvements in your picking. Like for example, in our example earlier, in S2 and S3, you can notice that S2 dominates S3. What we mean by that is everything in S3 is contained in S2. So there is no point in picking S3, because instead of picking S3, just pick S2, because you have all items of S3 and S2 anyway, right? So if a set or if a subset dominates another subset, then just choose the bigger subset, okay? Because everything in the other subset is contained in that one anyway. Yeah. So that's one improvement. And then another one, you might notice that only the subset S5 has the item 5, right? It's the only one that covers item 5. So that means that S5 is required, because you cannot cover everything without S5, because that's the only subset that covers this item. So by adding that restriction, you would have solved the problem more quickly. Okay, so those are some improvements that you can do for the set cover. So that's it for the part 1 of greedy algorithms. So we discussed activity selection, wherein you choose the activity that ends first, so ends early. Okay, so that is our greedy choice. And then for set cover, you choose the subset that has the most number of uncovered elements. Okay, so again, greedy is hit or miss. It could be optimal sometimes, it could be suboptimal sometimes, but at least it gives you something to start upon. Okay, so yeah, that's it. So this is end of part 1, and part 2 will follow shortly. Okay, we are now in part 2 of our greedy algorithms lecture, and in part 2 we will discuss how to apply the greedy strategy for Huffman encoding and fractional knapsack. Okay, so let's start with Huffman encoding. So it's not Huffman and then coding. Okay, so this is all about binary codes. Okay, so let's say for example you're given an alphabet or a set of letters. Let's call that sigma. Your task is to map each character to a binary string. Okay, so for example, if your alphabet only consists of 4 letters, A, B, C, D, you could how will you encode these 4 letters into binary code? Okay, so you could use since there's only 4 letters, then you can use 2 bits for encoding. So you could do something like this, right? So A would be represented by 0, 0, B could be 0, 1, C could be 1, 0, and D could be 1, 1. Okay, so you now have a binary coding encoding for each letter. So make sure that each binary encoding is unique, because you need to map the letter to the code, right? So if it's not unique, if it's if a coding or a mapping is the same, then it would be ambiguous, right? Because if both A and C are mapped to 0, 0, then you wouldn't know what 0, 0 means. Is it A or C? Okay, so it has to be a unique encoding. So if you were to encode BAD, for example, that would be 010011, right? So that's the binary code here. And then if you decode this binary code here, so 11 would be D, right? 00 would be A, and then 01 here would be B. So that would be DAB. Okay? So it's pretty straightforward to encode and decode your messages once you have the binary encoding. Okay? Now how about if we have small letters from A to Z as our alphabet? So we have 26 characters now. So how many bits or binary digits will we need to use? So if there are 26 characters, we will need 5 bits, because 5 bits can encode 32 binary strings. So that would be enough to encode 26. Okay? Why is it 5? Because 2 raised to 5 is 32. Okay? So if it's a binary string, right? Okay. If it's a binary string with 5 digits, 2, 3, 4, 5, then for each digit it could be 0 or 1, right? So there are 2 choices. So you could have 2 choices here, 2 choices here, 2 choices here, here, and here. So that would be 2 raised to 5 or 2 raised to n. Okay, so you can encode 32 binary strings. Okay, so if we have A to Z plus the big letters A to Z, that would be 26 times 2 or 52 characters. Now if we have 52 characters, it will not fit if we have a 5 digit encoding. So instead, we will use 6 digits naman, because if we have 6 digits, this could encode up to 64 binary strings, and that would be enough to hold the 52 characters. Okay, so in general, if you have n characters, you get the ceiling of the log of n base 2. Okay, so if you had what was that again, 26 earlier, log of 26 base 2 would be something like 4 point something, right? And then you get the ceiling of that, so this would be equal to 5. Okay, so you leave enough space at the top, so you have more extra digits. It's better to have extra digits, or sorry, extra binary codes that you don't need to use, rather than to have less than the required one. So you don't want to have a deficit. Okay, because if you just use, let's say, 4, if you get the floor of this one, if you only use 4, 2 raised to 4 will only have 16 characters, or 16 possible binary codes, and 16 will not cover all 26, right? So it's better to have more, like 2 raised to 5, 32. So 32 has enough to cover 26. So there will be 6 that will be unused, but that's fine. Okay? So once you have a fixed length encoding, just like what we did earlier, wherein each letter is mapped to, let's say, a code of length 2 or length 4 or length 5, it would be easy to encode and decode because there's a fixed length. So if you encode, you just follow the mapping itself, and if you decode, you can just break the string into the length, and then so for example, if there's a 10 digit binary message, and then the encoding is of length 2, then you can just divide it into 2s, right? And then there will be 5 letters there. So this is actually the same idea that's used in ASCII encoding. So something like this, right? If you're familiar with ASCII, so A is mapped to the binary representation of 65, B is to 66, and so on. Small a is to 97, and so on. So it's fixed length, basically, ang sa ASCII encoding. Now, we are doing the binary encoding because we want to well, digitize the information that we have so that we could send it over the wires, right? Communication through the internet. Our data has to travel digitally, so it has to be transformed into binary, so zeros and ones. And because we are trying to transfer this data, we want to save as many bits as possible, right? Because of course, the more data we send, the more costly it would be. So we want to be as efficient as possible in encoding the message so that it's the message is still intact, right? You don't lose any information, but you're using as few digits as possible. Okay, so we have a question here: is there a more efficient encoding that uses less number of bits to encode a message? So can we do that? So what if we don't use fixed length encoding? Okay, so can we do better than fixed length encoding? And yes, we can, because if you think about it, some characters appear more frequently than others, right? So there are some letters that are more common, whereas some other characters are quite rare, right? Like for example, A or E or I or O, those are more frequent letters, whereas letters like Q, X, V, those are kind of rare, right? So if you think about it this way, maybe you can use shorter codes for frequent characters because they are used frequently. So you need to have shorter codes for them so that if there would be a lot of these characters, you would have a shorter total, or yeah, a smaller total um, number of bits. Like for example, if we had a fixed length, if it was fixed length of 3, and then a message like A would have, well, 3 times 4, this would be 12. But if we did it based on frequency and A was only mapped to, let's say, one letter, let's say 0 ang A, then A would only have 4 characters, right? So 4 versus 12 is a very big difference. So you already saved a lot of characters just from reducing the number of bits for the frequent character A. Okay, so we can do it like this, and in turn, if we have shorter codes for frequent characters, we will also need longer codes for rare characters, because anyway they don't appear as much, so we could afford to give them a longer code. Okay, so we will base our decisions on character frequency. So that makes sense, right? If it's frequent, it appears more often, then use a shorter code. And then if it's rare, if it doesn't appear often, then you can use longer code, because anyway once in a blue moon lang siya mag-appear. Okay, so we can now discuss the idea of variable length encoding compared to fixed length encoding earlier, wherein each letter needs to be encoded to a binary code of a fixed length. Like for example, everything has to be of length 2, or everything has to be of length 5, something like that. So in variable length encoding, the binary codes can have varying length based on frequency. So this is what we talked about earlier. More frequent ones can get a shorter code, whereas rare letters can get longer codes. And our goal is to lessen the total number of bits used to encode the message, because we're trying to save as much data as possible. Okay. Now, variable length encoding is the same idea that's used in Morse code. So if you're familiar with Morse code, the more frequently used letters like T or E, those only have a short code, but longer or more rare, the rare letters like Q, Z, X, and V, they have a longer code, right? So they have 4 dashes and dots here, whereas A or E only has 1 and 2. Okay, so variable length based on frequency. So let's see another example. For example, if you have the 4 letters A, B, C, and we know that A and D appear more frequently than B and C, right? So we could do an encoding like this. So maybe we could encode A as 0 and D as 1. Okay, so shorter encodings for the frequent letters, and then 0, 1 and 1, 0 for B and C, because we gave them a longer encoding because they appear less frequently. So if this is the encoding, what do you think would be the decoded message for 0, 0, 1? Will it be AB, CD, or AAD? Or is it ambiguous? Okay, so let's try to figure this one out. If it's 0, 0, 1, it could be 0 here could be A, right? So that could be A, and then the 0, 1 here could be B. So this could be a possible answer. Could it be CD? Well, no, because it starts with 1, 0 and we don't have 1, 0 here, so this is not possible. How about AAD? Is it possible to be the message as well? Well, we can use A as 0, A again as 0, and then 1 as D. So it's also possible to have AAD as the answer. So this one is actually ambiguous. Okay? We don't know whether it's AB or AAD. Okay? So it could be AB, it could be AAD. So therefore the answer is it's ambiguous. And what was the problem here? The problem was if we have variable length encoding, it's not clear where one character ends and the next one begins. Okay? This is not a problem in fixed length codes, because let's say, for example, if going back here, if it was, let's say, length, let's say we have 0, 0, 1, 1. If it's fixed length of length 2, we can just divide it per 2s, right? So we can divide it per 2 and then decode each segment. But if it's variable length, if it's, for example, 0, 0, 1, we don't know whether the segmentation is 0, 0, and then 1, or could it be 0, 0, and then 1, or could it be 0 and then 0, 1. So there's a lot of many possibilities for how you can decode this one, because it has variable length. There could be length 1, there could be length 2 na digits. Okay? So our solution to this problem is to use something called prefix-free codes. So what does this mean? We have to make sure that no pair of encodings are a prefix of each other. So as an anti-example, let's use the previous example that we had, wherein we had a problem. So this one is not a prefix-free code, because the encoding for A, which is 0, is a prefix for B. B also has a 0 here. So you actually don't know whether, if you see a 0, is that solely A, or is that the start of the B encoding, right? The same thing for D. D has encoding of 1, and you're not sure if 1 is standalone D, or is that the beginning of C, which is 1, 0, because 1 here is a prefix of 1, 0. Okay, so we have to make sure that no pair of encodings are a prefix of each other, so that there is no confusion. So an example of a prefix-free code is something like this. So you could have A as 0, B as 1, 0, C as 1, 1, 0, and then D is 1, 1, 1. So if you see a 0, that's automatically A. If you see a 1, well, you're not sure yet, so you have to look at the next item. So if it's 1, 0, then that would be B. If it's 1, 1, that could either be C or D, so you have to look at the next letter, which is either, or next digit, which is 0 or 1, and that would decide if it's C or D. Okay, so this is an example of a prefix-free code, because none of the encodings are a prefix of each other. Okay, so Okay, so the idea of using variable length codes was because we wanted to save on the number of bits, right? So let's try to compare the average number of bits that we can use if we use fixed length versus if we use variable length. So if this was our encoding, fixed length, so we have length 2 for each one, okay? And given this frequency, what would be the average number of bits per character? Well, regardless of the frequency, it would still be 2 because anyway, for each letter, you'll be using 2 digits per letter. So the average number of bits per letter or character would still be 2, regardless of frequency. Okay? But if we use variable length encoding, like for example, the one that we showed earlier, so A is 0, B is 10, C is 110, D is 111, and given this frequency, let's say A appears 60% of the time, B appears 25%, C appears 10%, and then D appears 5% of the time, what would be our average number of bits per character? So how would we compute this one? You can pause the video for now and try to figure out whether the average number of bits is 1.5, 1.55, 2, or 2.5. Okay, so I haven't told you how to compute this yet, but try to think for your own how you would compute the average number of bits and try to see if you got the right answer. Okay, so we'll now look at the solution. So if this is the encoding and this is the frequencies, so for A, this is how we will compute it. So for A, this is the number of bits and this is the frequency. So number of bits, A only has one bit, and this appears 60% of the time, so this is 0.6. Okay, for B, it has 2 bits and it appears 25% of the time. And then for C, it has 3 bits. D also has 3 bits, right? So 3 each sila. And then C appears 10% of the time, and D appears 5% of the time. So if for A, what would be the average number of bits per letter? That would be 1 times 0.6, so 0.6 bits on average. And then for B, 2 times 0.25, so that would be 0.5. 3 times 0.1 would be 0.3, and 3 times 0.05 would be 0.15. So if you add all of this up, so that's 11, 14, plus, 1.1, 1.4, and then 1.55. Okay? So if you add all of that up, that would equal to 1.55. So what is this number? Earlier, we saw that the fixed length has an average of 2 bits per character. But on our variable length, we only have an average of 1.55 bits per character. So this one has a shorter average number of bits. So in general, you would also have a shorter encoded message, right? So hopefully now you can see the value of using variable length encoding. As long as it has a prefix-free code, you can use it to save data, okay? Because you'll have less number of bits per character in general compared to fixed length, okay? So it uses less bits per character, and that's what we want, okay? Because as I mentioned, the applications for this one could be saving network bandwidth when we send data over the internet or over the network. Same thing with compression for JPEG files, for PDF files, MP3, MPEG, gzip. So in compression, you're holding the same amount of data, right? So you should not lose any data, but you are trying to shrink the amount of space that you're using. So this is one application of variable length encoding, wherein you represent the data in such that no information is lost, but you reduce the number of bits that you're using in saving the data. Okay, so now that we know that variable length encoding is the way to go, how do we get the best variable length encoding? Okay, so for this one, we will be using binary trees. Okay, the concept of binary trees in variable length encoding. So we will represent our binary code as binary trees. So for our input, we could get the frequency of each character in the alphabet, because as we mentioned, we'll be basing this on character frequency, right? So more frequent letters that frequently appear will get shorter codes, whereas less frequent letters will have longer codes. Okay, so it could be the frequency or the probability of each character appearing. Okay, so it's more or less the same. And the output is finding the best prefix-free binary encoding for that alphabet. Okay, what is the best binary encoding? And by best, we mean that it saves it minimizes the total encoding length. So it will excuse me, try to minimize or save as many bits as possible. Okay, so that's what we're trying to look for, the best prefix-free binary encoding. So the binary tree is the representation of the binary encoding, and that is what we'll use. So examples of these types of encoding would be something like this. Okay, so for you can represent it like this as a binary tree. Okay, so A is represented here with a 0, 0. B is represented here with a 0, 1. C is represented here as a 1, 0, and then D is 1, 1. So you'll notice that all left children or left edges have the label 0, whereas the right children or the right edges have the label 1. So that is what we'll use as the pattern in general. Another example, this time it's a variable length encoding. So A is at here, just path from the root to A is 0. B is here, 1, 0. C is 1, 1, 0. And then D is 1, 1, 1. Okay. And then the bad example that we had earlier, the one that was not prefix free, it would be something like this. So A is 0, so it's found here. B is 0, 1. C is 1, 0, and then D is just 1. Okay, so what was the difference in the first three? So in the first two examples, we found the letters to be in the leaves, or the nodes that has no children. So these are the leaf nodes, right? A, B, C, and D. So they have no children anymore. Same here. A, B, C, and D are leaf nodes. But in example number 3, we found letters inside internal nodes, right? So A and D are internal nodes because they still have children. And if that's the case, then that would have the ambiguous encoding, because that would mean that A and D are prefixes of other encodings. Like A here is a prefix of AB because it still is an internal node. Okay, so your indicator of when you have prefix free encoding is when all of your letters are leaves already. Okay, so we don't want an ambiguous encoding wherein it has prefixes. So if we want prefix free encoding, all letters should be found in the leaves. Okay, no letters should be in the internal nodes, because a letter in an internal node would mean that it's a prefix for another subtree. Okay, so in prefix-free binary trees, each character in the alphabet has one node in the tree. So everything has to be part of the tree. Okay, and as I mentioned, the left child edges will have the label 0, and then the right child edges would have the label 1. Okay, so if you try to encode a letter, just follow the bits along the path from the root to the letters node, and that would be the encoding of that letter. Okay, and then if you decode, repeatedly follow the path from the root until you reach a leaf to get the letter of that of the current letter of what you're encoding. So let's see an example. To encode CAB, how would that look like? Okay, so CAB. So if you want to get C, so you'll follow the path 1. Okay, maybe red is better here. So the path is 1, 1, 0 going to C, right? So you'll have 1, 1, 0, So you're done with C. And then for A, that would just be 0. Okay? And then for B, that would be 1, 0. So another 1, 0. So that is how you encode your your CAB. So 1, 1, 0, 0, 1, 0. Okay? Now for decode, how about if we decode this message? So 1, 0, so that would be 1, 0, and then once you reach a leaf, you output the letter. So 1, 0 here is B, and then 0 is already a leaf, so that's A, and then 1, 1, 1 will reach here, which is D. So this will be decoded to bad. Okay, so that is how you use the binary tree to encode and decode your message. Okay, so the question now is, since we already know how to use it and we know that it's what we want, how do you actually build this prefix-free binary tree encoding? Okay, so the first idea that we could maybe think of, since it's building a tree, and building a tree kind of reminds us of divide and conquer, right? Using recursion, because the divide and conquer algorithms that we've seen so far all uses trees, or the recursion tree, right? And since we're building a prefix-free binary tree, maybe divide and conquer makes sense, right? Okay, so let's try the divide and conquer idea first. So in the divide and conquer idea, we would partition the letters into sigma sub 1 and sigma sub 2 with roughly 50% of the total frequency in each half. Okay, because in divide and conquer, diba, we divide the problem into sub-problems and then divide it even further until we can't divide it anymore. So we'll recursively compute the tree for sigma 1 and sigma 2, and then we'll repeatedly do this until everything has been solved. So this follows a top-down approach, right? So from big going to small. So let's say, for example, this is our frequency of the letters. Okay, we could divide it like this, wherein in sigma 1 there could be A and C. So A has a frequency of 5 and then C has a frequency of 1. So total nila is 6 ang frequency. And then for the rest, that would be B, D, R, and O with 2, 1, 2, and 1. So that is also a total of 6. So you'll divide it in a way such that it would be kind of balanced, right? So since there's 6 and 6 on both sides, we'll proceed with dividing them further. So A and C could start with 0, and then B, D, R, and O could start with 1. And then if you do this further, it could look something like this, right? So A and C could be in one side, B, D, R, and O could be in another side. Then if you divide them, A could be in one side, C could be in the other side. And for B, D, R, and O, you could divide it like B and D on one side so that it has frequency of 3, R and O on one side, frequency of 3 as well. And then divide them further like this. So you could have your prefix-free binary tree like this if you use divide and conquer. And the idea again is divide into 2 at each level. The height of the tree would be log of n base 2, right? Just like our previous recursion trees. And the length of encodings are roughly the same because they won't be too far apart from each other because you're dividing it into half. Okay? So this is actually the idea behind Shannon and Fano algorithm. So it's a divide and conquer algorithm for prefix-free binary trees. And Shannon and Fano are actually pretty prominent people because Claude Shannon is known to be the father of information theory, while Robert Fano was Huffman's teacher. So, diba, we're supposed to be discussing Huffman encoding, but up to now, we haven't encountered Huffman yet. But Robert Fano is actually Huffman's teacher in his postgrad. So, this turns out to be a suboptimal solution, ang divide and conquer algorithm nila. So, imagine that, even the father of information theory, his algorithm turned out to be suboptimal. So, the optimal solution was to use the Huffman encoding created by David Huffman, who was a PhD student at MIT at that time. So, he was under Fano of the the Shannon-Fano algorithm. So he was the teacher, and he just created this for a term paper for his information theory class in 1952. So he created this algorithm or this encoding as part of his requirements. Okay, so in his encoding, the idea is not to use top down like divide and conquer, but to do it in a bottom up manner. So he uses successive mergers to merge two letters together, or two symbols. So you merge symbols to form a parent node, and then after that, once you've merged them, you repeat it until all symbols are merged already. Okay, but the question here is, which symbols do we merge? Okay, so let's think about it this way. If you have a greater frequency, you need to have a shorter encoding, right? That's what we want. And if you have a lower frequency, you can have longer encoding, because anyway you appear less frequently. So which one should we merge first? So a long encoding will have a longer path to the root, from the root to the node, right? So like for example earlier, if we go back to this one, okay, so A has a short encoding, so it has a short path from the root to A, but D, for example, has a long encoding, so it has a longer path from the root to D, to the leaf. And that is because it has a lesser frequency. Okay, so if that is the case, then which symbols do we merge? Okay, should we merge the greater frequency first or the lower frequency if we want longer encodings to have longer path to the root? Okay, so pause it first and try to choose between the two. Which one do you think should we merge first, greater frequency or lower frequency? Okay, so for Huffman encoding, the greedy heuristic that we will use is we will merge the two symbols with the lowest frequencies. Okay, so those that appear less will be merged first. And the reason for that is because we'll merge them first, they will have a longer path to the root. So we'll see that in the example later. Okay, so lower frequency symbols can have longer path in the tree and therefore can have longer encoding, so we will merge them first. Okay, whereas high frequency symbols should be merged near the root for it to have a shorter path and a shorter encoding in turn. Okay, so when merging symbols A and B, we will replace the symbols A and B with a new symbol AB. So it will be like a proxy, a merged version of the two. And then we'll continue merging with AB this time, not A and B separately. Okay, but once we've merged them, what do you think should be the frequency of AB? Should it be the max frequency between the two? Should it be the min frequency? Should it be the sum? Or should it be the product? Okay, so what do you think? What should be our representative frequency of the new merged node AB? So, for example, if A and B here, this one has a frequency of 3, this one has a frequency of 5. If we merge it to AB, what should be AB's frequency here? Should it be max, min, sum, or product? Okay, again, try to answer this one first before going to the next slide. And the answer is, you get their sum. Okay, why will we get their sum? As I mentioned, AB is a proxy for A or B. So if it's A or B, so it appears A times plus B times. Okay, so you need to get their sum, so the total frequency. So if you put all of that together in a pseudocode, it will look something like this. So you're given all the nodes. The nodes are all symbols in the alphabet, and while there is still nodes left, so while it's still more than one, okay, so we'll only stop if there's only one node left. So the right node will be the minimum frequency node, and then the left node would be the next minimum frequency node, and then we will merge them. So the left symbol plus the right symbol will be the parent nodes label. Okay, so we'll just combine their labels, and then the left child would be the left node, and then the right child would be the right node. So, and then the frequency of the parent would be the sum of the frequency of the left child and the right child, and then the parent would be added to the nodes, while the left child and the right child will be removed from contention, and then we'll repeat this until all nodes have been processed. Okay, so if you're given n letters, then there would be at most n minus 1 merges, or O of n iterations, because we will stop only if there is only one node left. Okay, so there would be at most n minus 1 merges, so that would be O of n iterations. If we are trying to find the node with minimum frequency, we have to loop through all the letters, and that would also take O of n, because you have to look at everything, right? So that would be O of n as well. So if there are O of n iterations, and per iteration you have to find the minimum, which takes O of n, so the total running time is O of n squared. Okay, so the running time is O of n squared. Memory is O of n, because we need the extra memory for holding the nodes for the binary tree. Okay, this can be improved by using a priority queue, but for now we'll just use a the basic na binary tree. Okay, by using a priority queue, you don't have to find the min at each time. You could just use the front item in the priority queue. Okay, so now to create the encoding, this is a more detailed version of the pseudocode, right? So nodes.pop, if node has no children, then the encoding of this for that symbol would be the encoding of the node. Okay, so meaning it's already the leaf node, and then left encoding will be +0, right encoding will be +1, and then we'll add the left and right nodes to the nodes, basically. So this will create the actual encoding from the tree. So given that you have, let's say, something like this, like if you have something like this, so A, B, C, D, so we'll label this as 0, 1, 0, 1, 0, 1, right? So all left children would have 0, all right children would have 1. So how would we get the actual encoding from this tree? Okay, so basically we'll just traverse all nodes. So from A here, from the root, let's go to the right child, and since A has is a leaf node, then we'll get its path, which is 0. So A is 0, and then for B, you have a 1, and then to the 0 here. So since B is a leaf, B would be mapped to 1, 0, and then from 1 here we go to this child. So we currently have 1, 1 now, and then we go to the left, we get C, which is 1, 1, 0, and then to the right we get D, 1, 1, 1. So this is how we get the actual encoding from the binary tree. We'll just need to traverse all nodes and then get their respective paths going from root to that node. Okay, so for creating the encoding, there are n leaves in total, n letters, and then n minus 1 internal merges. So that would be 2n minus 1 in total, but still O of n, right? So the running time is still O of n. So it's still linear time ang pag-create ng encoding. Okay, so let's now look at an example wherein we have these frequencies for A, B, C, and D. Okay, so these are our frequencies. So first thing that we'll do is we'll sort them by frequency in descending order, but this one is already sorted. So the first merge that we will do would be the first two, the two least frequent items, and that would be C and D, because they're bottom two currently. So 10 and 5 would be merged, so the new node would be CD, and it has a frequency of 10 plus 5, which is 15. So that would be our first merge, and we now have removed C and D. We now added CD. So the next thing that will merge would be B and CD, because those are the two with the least frequent less frequency, so 25 and 15. So we'll merge that, and that it will become BCD with a frequency of 25 plus 15, 40. Okay, so that would be our second merge. And then finally, we have 2 items left, so we'll merge those 2. So it will become ABCD with a frequency of 100. And since there is only 1 node left, we are done. Okay, so after doing these merges, how would the binary tree look like? Well, it would look something like this. Okay, so C and D, we merged that first, so it became CD. B and CD, we merged that to become BCD. And then A and BCD, we merged that to become ABCD. So the left children has 0 label, and then the right children has 1 label. Okay, and then for the total bits, how do you compute the total bits? A, okay, so A has an encoding of 0, so it only has 1 bit, right? Times 60, so 60 bits in total. For this one, it has 2 bits, and then times 25 ang frequency niya, so you have 50. 3 bits times 10 would be 30. And then 111 times 5, so that's also 3 bits times 5, which is how much? 15. So if you, this is 30, not 38. So in total, that would be 155 bits in total ang frequency niya. Now, what would have happened if we used fixed length encoding? If it's fixed length, we can use length 2, right? Because there's only 4 letters, so we could have the 00, 01, 10, 11 for A, B, C, and D. So if it was 2 ang encoding niya, so A, B, C, D will have length 2, all of them will have length 2, and then the frequency is 60, 25, 10, and 5. So this would have 120, 50, 20, and 10. If we sum all of that up, that's 5, 6, 7, 8, 9, 10, 200. So we'll have 200 bits for encoding this letters, compared to variable length wherein we only have 155. So we saved about 45 bits for this encoding. Okay, so that is how you do Huffman encoding. So you just select just select the two least frequent nodes based on frequency, merge them, and then repeat, merge, repeat, merge, and then build the tree by putting the left children with 0 and then the right children with 1. Okay, so that is Huffman encoding. 155. Let's see one more example, this time for abracadabra. So if it's abracadabra, if this is the message, let's try to figure out the frequency. So A appears 5 times. We have 1, 2, 3, 4, 5, right? B appears twice here. C appears 1 time. D appears 1 time. R appears twice here and here. And then the exclamation point appears 1 time. So exclamation point is included because that's also a symbol. So given these frequencies, okay, let's try to find out the best prefix-free encoding. So let's sort them by their frequency descending. So they're now sorted. So we'll pick D and exclamation point first. So they will have a frequency of 2. Okay, and now the next 2 least frequencies are C and the merged one, D exclamation point. Okay, so it will now have a frequency of 3. So it now moved up because frequency 3 siya. And then the next 2 that will merge would be B and R, total of 4. Then the next would be the B and R and the D, C. So it will have 7. And then finally, this 2 would be merged. And then since we only have 1 node left, then we're done. So based on this would be our encoding. So BD, everything here. So we started with the D and exclamation point here, right? And then D was added with C. So it's here, and then B and R was here, and then they were merged to BRDC, and then A was added last here to form this. So just follow the left merges and the right merges for the label for it to be consistent. Okay, so that is Huffman encoding. And yeah, so fixed length would have 36 letters because of the there's 12 letters, and then if there's 3 bits per letter, it would be 36. For variable length, as we saw earlier, it only has 28, right? So we also saved a few bits. Okay, so that is Huffman encoding. Let's now go to our second problem, which is fractional knapsack. So if you remember the knapsack problem from dynamic programming lecture, it's more or less the same, but this time, imagine that the robber or the burglar can steal gold dust instead. Okay, so for 01 knapsack, imagine that he was stealing gold bars, so he should either take the gold bar or not. But here, in fractional knapsack, imagine that he's stealing gold dust. Okay, so within the whole bag of the gold dust, he can take that, or he could also take only part, like scoop up some gold dust, if that is what will fit the knapsack. Okay, so in fractional knapsack, we either take the whole item or a fraction of the item. So that means that the item could be breakable, or yeah, it's not a solid whole. Okay, so for the input of the fractional knapsack, it's the same as the previous knapsack versions. It will still have capacity W. We'll have n items, wherein each item has a weight and a value specified. And then for our output, we will give the percentage of each item. So how much of that item will we take? So the percentage ranges from 0 to 1. And then it could be a fraction of that one. So if you don't take the item, it would be 0. If you take the whole item, that would be 1. And then if you take only a portion of the item, then you specify the percentage. Okay? And again, the same restrictions apply. The total weight of the items should fit the capacity, and we're still trying to maximize the total value possible. Okay? The only difference now is that you could take a percentage of the item. Okay, so let's go straight to the greedy approach. We could greedily pick the item, of course, and then if the whole item can still fit, we could take the whole thing inside the bag, then take 100%, because we're being greedy, right? Since we could still fit it, just take the whole thing. But if it cannot fit anymore, then just take the fraction of the item that will fit the knapsack, and then you can stop. Okay? But again, the crucial question here is, how do you greedily pick the item? Which item should you pick first? So we have a few heuristics. So what should be the order in picking items? Should it be decreasing value, increasing weight, decreasing value times weight, or decreasing value divided by weight? So when you say decreasing value, you start with the one with the most value first, right? The most expensive one. If it's increasing weight, you start with the lightest item, right? And then decreasing value times weight, so take this product and take whatever is the biggest score. And then the same thing for value over weight, you take whatever is the biggest score and then go in descending order. So before you go to the next part, try to figure out first whether A, B, C, or D is the best heuristic to use. Okay? So let's go through each one and discuss why they could be appropriate or not. So let's start with decreasing value. So in decreasing value, we will pick the item with the highest value first, right? So the most expensive value, we'll put that inside. This one is suboptimal. And which scenarios could this be suboptimal? There could be instances wherein the item has a big value. So yes, it is expensive, but it's very heavy. Okay? And you would have been better off if you chose two lighter items but with a bigger cumulative value. Okay, so let's see a counter example to that. Let's say that our total capacity is only 5 kilos. And then we have item A, 10 peso, 5 kilos. Item B, 6 peso, 3 kilos. Item C, 5 pesos, 2 kilos. If we use decreasing value, so we'll pick the most expensive one first. So the most expensive among the three would be A because it costs 10 pesos. But A would already fill up the whole knapsack of 5 kilos, right? So you would have no space left. And if that's the case, your greedy solution will only get you 10 pesos because you only have A. But what would have been the optimal solution? The optimal solution would have been taking the two smaller items, B and C, which also fits the 5 kilogram capacity because this is 3 plus 2, but their total cumulative value is more than 10, which is 11. So decreasing value is not optimal for all cases. Okay, so we won't choose that one. Now how about if we pick the item with lowest weight first? Because in the previous one we had a problem because this one was too heavy, right? And it filled up the capacity of the knapsack right away. So what if we pick the item with the lowest weight first, right? Maybe that would leave more room for other items to be fit in. But is this optimal? Okay, it's not. So which scenario would this be suboptimal? So it could be that the item is light, but it also has a small value, right? So you would have been better off if you took the heavy item that has more value. So a counter example would be this one. So again, we have a 5 kilogram capacity. A has 2 kilos with 3 pesos, B has 3 kilos with 5 pesos, and C has 5 kilos with 10 pesos value. So if we choose increasing weight, we would choose the one with least weight first. So that would be A, right? And then if it's A, then we would choose 2 kilos with 3 pesos. And then after that, you're left with 3 kilogram space. So the next one that you'll choose between 3 and 5 kilos would be 3 because you're going about it in the increasing weight order. So this one is the next smallest item, so you would take the whole thing since it can still fit, and that would take up the whole 5 kilos. But the total value would only be 8, whereas the optimal value would have been taking C for the whole 5 kilos and getting 10 peso cumulative. Okay? So increasing weight also does not work all the time. So the best heuristic that you would have used would be something, okay, so your ideal item would be something that has big value, right? It's expensive, but it also has small weight. So it's expensive, but it's also small. And that means that you have more value and you have more space to fit other items. So that is your ideal item. And this ideal scenario is being encoded in the equation value over weight, or value divided by weight. So this will maximize that score, because if you have a big value, if you want a big value, then you want value to be a big numerator, right? If you have a big numerator, you'll have a big score. And if you want a small weight, then you put it at the denominator, because if you divide it by a small number, that will also give you a big score, right? So for example, if you have a let's say value of 10 peso and it only has a cost of a weight of 2 kilograms, that would be 5 peso per kilo. Okay, and then if you have, let's say 20 peso but it's also 10 kilos, that would only be 2 peso per kilo. So you're actually getting the value per weight. Okay, the pound per pound, which one has the best value. Okay, so this will give us the optimal solution this time. Okay, and the idea for why this will give us the best answer is because we're getting the item with highest value per kilo. Okay, so for example, if you have heavy plus and it's cheap, then that will have low priority because you're already heavy, you're taking too much weight in the knapsack, and you don't contribute too much in the total value, so you'll have low priority. If you're heavy but you're also expensive, you'll have middle priority. Same with light but cheap. Okay, because those two values offset, right? If it's heavy, it takes too much space, but it's also has big value, then it's pretty you can live with that consequence. You can live with that choice, right? It's tolerable. And then if it's light, or if it's cheap but it's also light, so it doesn't take up too much room, so at least it still contributes to the total value, then it's also tolerable. But what you really want is the light items that are also expensive, so that will be given high priority. Okay, so for this one, let's see what would be their scores. So the score for value over weight would be 10 peso over 5, that would be given a score of 2. 6 over 3 would be given a score of 2, and 5 over 2 would be given a score of 2.5. No, that's not it yet. So for our greedy, we would take this one first, C, right? Because that has a score of 2.5, and then either B or A, right? Because it has a score of 2. But since our weight is 5, then maybe we'll pick this one, so that would be 2 kilos plus 3 kilos, so that would be 5 kilos, and then total of 11. But it could also have been C plus so we already have 2 kilos here, so we only have 3 kilos left of free space. If we chose this one, since they have the same score anyway, we can only choose 3 out of 5 kilos of A, because taking the whole 5 kilos will not fit anymore, right? If it's 3/5 of A, that would be 6, 3/5 of 10 pesos would also give you a value of 6 pesos, so that would be 6 plus 5 as well, with a total cost of 11. Okay, so it would be the same. Okay, so it has two optimal answers, because anyway they were tied in the score. Okay, now for this one, we'll compute their score. So value over weight would give you 3 over 2, that would be 1.5. 5 over 3, that would be 1 2/3 or 1.67, and then 10 over 5 would be 2. Okay, so given these scores, we would pick C first, right? So we will pick C with 5 kilos and 10 peso value, and then since it already takes up the whole 5 kilos, then that's it, right? We can't add A and B anymore. Okay, so putting all of that in pseudocode to look something like this. So we'll initialize the percentage to start at 0 for each item, and then the current free space would be our current capacity. So this will be reduced to 0 eventually, but we'll start with the initial capacity. And then the item that we'll choose first would be the item with maximum value over weight. And then if that item's weight is still less than or equal to the free space, or it still can fit, then we'll get 100% of that item, and then we'll update the free space. But if it cannot fit anymore, the whole thing, then we'll just get a percentage. So whatever free space is left out of the item, and then of course the free space will be set to 0 because there is no more free space. Okay, and then we'll return the percentages for each item. Okay, so the worst case scenario would be if all items are selected, so that would take all n iterations, that would be O of n, and then per iteration we're trying to find the item with the maximum score, so we'll try to loop through all items, so all n items, so that will take O of n. So if there are n iterations, and then per iteration we have O of n work for finding the max, that would take O of n squared in total. Okay, So running time is O of n squared. Memory is O of 1, constant, because we're not using extra memory. The percentages here is not extra memory because this is our output. Okay, this is what we need to return. So this is not extra memory because that is part of the problem. Okay, so how about for this example? Is this the one? No, it's not yet that one. So let's try to solve this manually. So what would be their scores? So their score, if it's value over weight, so 2 divided by 1 would be 2, 4 divided by 3 would be 1.33, 3 divided by 3 would be 1. So we would pick A first. So select A, and can A still fit 5? So our capacity currently is 5. So A can still fit, so we'll get 100% of A. So 2 kilos with 2 peso value. So since we took 2 kilos, this would become 3 kilos na lang. And then the next best score is B with 1.33. So we'll take B, but can 3 kilos still fit? Well, yes, it can. So we'll take 100%, 3 kilos, and it will have a total value of 4. So if we take 3 here, it would be empty with total value of 6. Oh, wait. Sorry. This one was wrong. Supposedly A had 1 kilo lang. Mali. So 1 kilo lang ang A. So this would have been okay. Sorry for that confusion. So 5 minus 1 would have been 4, and then if we took the 4 minus 3 kilos here, that would have been 1. So there's still 1 kilo left. So we could still take C, that's the last item, but we cannot take the whole 3 kilos. We can only take 1/3, right? Or 33%. So because there's only 1 kilo free space left. Okay, so we'll only take 1 kilogram. That would be 1 peso as well, because 1/3 of 3 is 1. So 6 peso plus 1, that would be 7 pesos. So the solution would be take the whole of A, the whole of B, and then 1/3 of C. Okay, so yeah, sorry for the confusion. And then let's take a look at this one. I think this is, yeah. So if we have capacity 50, and then these are the values, and then the weights, or sorry, this is the value and then this is the weight. So the current capacity is 50, and then let's compute the score, value over weight. So they will have, this one will have a score of 6, this one will have a score of 5, 120 over 30 is 4. Okay, so based on the scores, we will take the best score, A, right? Score of 6. The weight is 10, so that can still fit 50. So we'll take 100% of it. Okay, and then new capacity will become 50 minus 10, which is 40. Okay, so we'll take 100% of A, and the next best score will be B, right? So B has a score of 5, so we'll take that one. Can the weight 20 still fit 40? Yes, so we'll take 100%, and we'll update the current capacity to be 40 minus 20, which is now 20. And then the last item would be C, but the full 30 weight cannot fit inside 20, so we'll only take 2/3, right? 20 out of 30, so that would be 67%, and then the new capacity would be 0. So we are now full. Okay, so this is now our final answer. We'll take 100% of A, 100% of B, and 67% of C, and the total value is 240. So this is 160 plus the 80 here would be 240. Okay, so yep, that's it. Now, using this greedy heuristic, would this have worked also on the 01 knapsack? Let's see. If it was 01 knapsack, okay, let's say that this is our scenario. We have 1,000 kilograms capacity, and then we only have 2 items. So one has 2 pesos worth with 1 kilo, and then 1,000 peso 1,000 kilo. But take note that this is 01 knapsack, so you could either take the item or not. There is no fractional anymore. Now, would this heuristic have worked as well? If we used this heuristic, which one would have been the answer? Okay, if we used V over W, what would have been the score for A? For A, VW would be 2, right? 2 divided by 1. But for B, that would be 1,000 over 1,000, so this would be 1. So based on the heuristic, we would choose A first, right? And if we choose A first, we would get 2 peso value for 1 kilo. So we are now left with 999 kilos of free space. But the next item cannot fit anymore, right? Inside 999, because this is 1,000. And since it's 01, we either take it or not. And since it cannot fit, we cannot take it anymore. So therefore, for greedy, this would only give you a value of 2 pesos, right? Because you can only take A. And the optimal answer would have been, of course, just take B for 1,000 kilograms and a 1,000 peso value, because 1,000 can fit the capacity. So this would have been the correct answer. Greedy is 2, optimal is 1,000. Okay? So we did not get the optimal answer when we chose the greedy heuristic 401. Okay, so but maybe we can try to patch the heuristic or maybe fix the heuristic, right? So what if we tried doing this? Maybe the first choice is the item with max value over weight, so the original heuristic, or what if we get the maximum value that can fit? Okay, and then we'll return whichever has the best choice, the max between the two. Okay, so what if we do it like that? So I'll write it down, our heuristic. So either max na value over weight or the max value that can fit. Okay, so we'll choose between the two. Okay, so if that is the case, what if we have this example? So 1,000 weight capacity, and then we have two items, A and B, with 2 and 1, 1,000, 1,000. So if that is the case, if this was the previous problem, we just tried to reapply the patched heuristic, the maximum value over weight is still A, right, with 2 peso, 2 over 1 score, but the maximum value that can fit is B with 1,000 peso value. So we'll choose B here because it has more value. So for this problem, we kind of fixed it. We got the optimal answer. But what if we get another problem like this? So this time our weight is capacity still 1,000, and then we have 3 different items, so 501, 502, 500, 500, 500, 500. So the value over weight here, this would be value 501 over 502, so this would be around 0.99, right? And then this one would be 1.0, 1.0. Okay, so if we get the best if we get the max value per weight, value over weight, that would be either B or C. So let's say B with value of 500. What is the maximum value that can still fit? Well, A can still fit, right? Because it has the maximum value of 501, and it can still fit because 502 can fit 1,000. So since it has the most value right now, A has the most value with 501. And if you get the max between the two, we'll still choose A because it has more value of 501. Right? So if we choose A, you get 501 value and 502 kilos. So you're now left with 498. But none of the two can fit anymore, so you'll just be left with A as your final answer. So even if we use the new greedy heuristic, when we patched it, it's still not optimal, right? It's still 501 lang ang value niya, but the optimal value would have been 1,000 if we took these two, right? B and C would have fit 1,000 and the total value would have been 1,000 pesos. Okay? So even if we patched the greedy heuristic, it still did not work for all cases. Okay? So for the knapsack problem, we already mentioned that the optimization version of the 01 knapsack is NP hard. Okay? So the dynamic programming algorithm and the greedy algorithm only worked for special cases. So the dynamic programming worked because the weight was small, and then for greedy, it worked because it was fractional. We could take part of the item. Okay? So for DP, because the test cases are relatively small, we could enumerate everything. And for greedy, we could take fractional parts, so that is kind of bending the rules of the original problem. So because they are special cases, then they work. But for the general version, knapsack is still NP hard. Okay? So that's it, and that's it for greedy algorithms. So to review, we discussed activity selection, wherein we pick the activity that starts or that ends first, so ends early, okay, so that we have more time to do other activities. For set cover, we chose the subset that uncovers the most number of elements, right, so that we could cover more items faster. Then for Huffman encoding, we merged the two least frequent items first, right? And then we merge them until only one node is left. And then for fractional knapsack, we take the item with the maximum value per weight. Okay? So greedy algorithms is all about choosing the right heuristic to get the optimal solution. Okay, but again, remember that greedy is hit or miss. In some problems, it could give you the optimal solution, but it's not guaranteed to work all the time, because in greedy, you're only taking the locally optimal choice in the hopes that it is also the globally optimal choice. Okay, so that's it for greedy algorithms. If you have any questions, please don't hesitate to ask, and I will see you in the next lecture.